Good afternoon, students. Welcome to the lecture 12 of Unit 2, that is Vapor Compression Refrigeration Systems. So, in the yesterday's class, we have discussed about the various components of vapor compression refrigeration systems, right? And also some of the problems related to the vapor compression refrigeration system. Today in this class, we shall discuss about the other topic, that is the simple or standard vapor compression refrigeration system, right? Simple or standard refrigeration system. Yes, we'll switch on to the slide. So in this simple vapor compression system, so the difference between the standard or simple versus vapor compression simple system is shown in this figure, right? So see here. So in the vapor compression system, as already we said, most commonly used for the domestic purpose, commonly used among all the refrigeration systems, right? So commonly means where you are using the domestic, that is home appliances, and also for shops to store the beverages, that is cool drinks. Vapor compression refrigeration systems are most widely used among all refrigeration systems. The name says general class of vapor cycles, where the working fluid is a refrigerant, that is freon 22. So in this vapor compression refrigeration system, we are using the working fluid called refrigerant. So the names of refrigerant we will see in the unit 3 detailedly, but the general type of refrigerants are freon 11, freon 12, freon 21, 22, fluorocarbons, like this. We are having some of the names related to this refrigerants. So these refrigerants, what they will go phase change. So then phase yokka, then పరిమాణం, the phase will get changed from vapor to gas, from gas to the air, like that, right? Phase change at least during one process. So in vapor compression system, the refrigerant is obtained as a refrigerant, evaporates at lower temperature. So a temperature it will get evaporated, so it will get evaporated at very low temperatures. So whenever the cycle is processing, that is 1 to 2, 2 to 3, 3 to 4, and 4 to 1, so here the refrigerant evaporates at lower temperatures. Now the input to the system is in the form of mechanical energy. So how we are giving the input to the this refrigeration system? We are giving in the form of mechanical energy required to run the compressor. So in a AC, in a refrigeration system, generally we are having compressor which is placed at the bottom. So how this compressor is run is, it is running by the use of current with the help of mechanical energy, right? The input to the system is in the form of mechanical energy required to run the compressor. So the systems are also called as mechanical refrigeration. So whenever you are using this compressor as a mechanical device, so we are calling them as mechanical compressor, mechanical refrigeration systems. So the vapor compression systems are available to almost all type of applications, required from watts to few megawatts. అంటే ఇవి ఇండస్ట్రియల్ టైప్ ఆఫ్ అప్లికేషన్స్లో we should not use vapor type of compression system. So that's why for almost all domestic applications, we are using the vapor compression refrigeration, standard vapor compression refrigeration system. Okay, so starting from అంటే watts నుంచి megawatts వరకు range వరకు we can manufacture our own refrigeration systems. That is informing like that. Next, a wide variety of refrigerants can be used in the system at different applications. The actual vapor compression cycle is based upon which cycle? So ఇది ఒక గుర్తుపెట్టుకోండి, the actual vapor compression system is based upon Envas-Perkin cycle and Evnas-Perkin cycle, which is also called as reverse Rankine cycle. So reverse Rankine cyclic, what is the other name? Reverse Rankine cyclic, the other name is Evans-Perkins cycle, or for Evans-Perkins cycle, what is the other name means reverse Rankine cycle. Understood? Reverse Rankine cycle. Next. So if you see the compression type, so we are having two types of compression system in the mechanical refrigeration system. One is dry type of refrigeration system. Other one is wet type of refrigeration system. Got it? So dry type and wet type. So here the figure shows involves the compression of wet refrigeration at 1 dash to dry saturated vapor at 2 dash. So whenever the split window is on the outside of the room, so if I keep, so the difference between the temperature and entropy. So obviously the comparison of refrigerant vapor, see here the temperature is on x-axis T naught and Tk, right? So the entropy is on the x-axis. See here. So the wet car refrigerant vapor at 1 dash to the dry saturated vapor at 2 dash. So whatever the compression takes place at 1 dash and 2 dash. At 2 dash, it is called as wet compression. With the reciprocating compressor, the wet compression is not found suitable due to the following reasons. So it is just only the paperwork of giving the capillary compression, or else it will be in a different form. See here, so 1 dash to 2 dash, it is passing 2 dash to px po. So start continuing along with the 2 and 2 dash, 2 and 2 dash. So wet compression is not found suitable due to the following reasons. So what are the following reasons? So it doesn't mix with the other things, right? So the next topic to be discussed is standard or simple vapor compression system, right? SVCR, or standard vapor refrigeration system. So in the last slide we have discussed it is based upon Evans, right, or reverse Carnot cycle. So here the Carnot refrigeration cycle is completely reversible cycle. So as already discussed in a few last classes, the Carnot cycle is completely a reversible cycle, but used as a model of for a model of perfection, a model of perfection for a refrigeration cycle, operating between a constant temperature, heat source and sink. It is used as a reference. So what it is using, we are using this as a reference against which the real cycles are compared. Okay, against which the real cycles are compared. So corner refrigeration is completely reversible cycle where it is used for this vapor compression refrigeration system. So the figure shows here. See the figure? The figure. So the compressor, wet compressor, the work is inside the compressor. From here it is going to the condenser to the expansion valve. From here the balance, the refrigerant is passing to the evaporator and it is evaporating outside to the atmosphere. So this is a process happening in the first diagram. The second diagram gives whatever you are discussing about in the previous slide. So it is a temperature entropy and there is a temperature and settlement, right? So now we'll start how to demonstrate this one. So the figure shows a basic refrigeration system with a vapor consists of four elements with four pure vapor which has a four components. So that is a physical devices or compressor, condenser, expansion device and ఎక్కడికి వెళ్ళకూడదు. So what are the four devices you are having? The compressor, condenser, expansion, and evaporator. The refrigeration effect Q plus 1 is equal to QE is obtained from the evaporator as a refrigerant undergoes the process of vaporization. Therefore, the process Q1, therefore, the process Q1 plus 1 is equal to QE is obtained by the evaporator as a refrigerant undergoes the process of evaporation or not.
Hello, sir. Hello, sir.
Yes. Now see this one. So the figure shows the refrigeration effect is obtained at the evaporator. At the evaporator is the final one where the refrigerant is going outside in the form of gaseous form. As the refrigerator undergoes a process of vaporization process, that is 4 to 1, and extracts the latent heat from the lower temperature heat source. The low temperature, less pressure vapor is then compressed isentropically in the vapor to the heat sink at the temperature Tc. The refrigerant pressure increases from evaporator to the compressor during the again compressor process. So here what's happening, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So whenever the refrigerant gaseous form లో ఉండి వేపరైజ్ అయిపోయిన వెంటనే అగైన్ ఫ్రమ్ 4 to 1 అగైన్ ఫ్రమ్ 4 to 1 నుంచి 1 to 2కి వెళ్తున్నప్పుడు అగైన్ ఇట్ ఈస్ గెటింగ్ increased, again it is getting increased for the compression process, right? Now the process 1 to 2 and the exit vapor is saturated. So whenever the 1 to 2 process and 4 to 1 process is getting saturated, the next the high pressure high temperature saturated refrigerant undergoes the process of condensation in the condenser as shown in the heart of the condensation to the external heat sink Tc. The high pressure standard cycle is then flows through the expansion device and undergoes isenthalpic throttling process. So here the temperature and pressure fall from compression to the expansion. Therefore, in the expansion device, the liquid flashes into the vapor. So at the third stage, ఏది 1 to 2 నుంచి 2 to 3, 3 to 4 అంటే 3 to 4 టైంలో the liquid vapor refrigerant is splashed. That is, it will flashes into the vapor and the exit condition lies in the two phase region. సో ఇక్కడ ఏం జరుగుతుంది, లిక్విడ్ నుంచి వేపరైజ్ అయ్యేటప్పుడు సో వన్ ఫామ్ నుంచి అదర్ ఫామ్ కన్వర్ట్ అవుతుంది. బట్ ఇన్ బిట్వీన్ వాట్ యు ఆర్ సీయింగ్ లిక్విడ్ ఫ్లాషెస్ ఇంటూ టూ ఫేస్ రీజియన్. అంటే లిక్విడ్గా ఉన్నది వేపర్గా మారిపోతున్న reaction you can see there, right? Next, expansion device, so that the amount of flashes into the vapor and the exit condition lies in the two phase region. The low temperature and low pressure liquid mixture that enters the least completing the device. Okay, Next, the figure shows the schematic of a standard saturated single stage. So standard, we can say it as a standard saturated single stage vapor compression system and the operating of TS diagram. The figure is a standard single stage consists of the four processes. Okay, what are the four processes? The four various processes are, see, the first one is I process 1 to 2, isentropic compression of saturated vapor. Isentropic compression of saturated vapor in the compressor. Next, 2 to 3. 2 to 3 is isobaric heat rejection in condenser. So 2 to 3 లో ఏం జరుగుతుంది? హీట్ అనేది రిజెక్షన్ జరుగుతుంది, ఐసోబారిక్ హీట్ రిజెక్షన్ ఇన్ ద కండెన్సర్. నెక్స్ట్ 3 to 4 ఐసెంథాల్పిక్ ఎక్స్పాన్షన్ జరుగుతుంది. అంటే in this process what happens, the liquid vapor is converting into the vapor form. Isenthalpic expansion of saturated liquid in a expansion device. Next 4-1 లో ఏం జరుగుతుంది? In the 4-1 isobaric heat extraction in the evaporator. So in the 4-1 what happens, the liquid refrigerant is converted into vapor form in the evaporator, thereby the heat is extracted, in the evaporator, so these are the four simple processes of simple vapor refrigeration system. అర్థమైందా? simple vapor refrigeration system. Next, see here. So from 1 to 2, the work in the compressor, mechanical pressure, mechanical system, the refrigerant is passing from the compressor to the condenser. From the condenser it is going to the expanding device. So here what happens, here the liquid refrigerant is converted partially into the vapor form. ఏది ఇక్కడ, from the expansion device it is going to the evaporator. So ఇక్కడ పోయినప్పుడు ఏం జరుగుతుంది, completely the liquid is completely converted into the liquid form, vapor form, and it is evaporated to the evaporator. Here the heat is extracted, right? So if you see the TS diagram, the 1 to 2, this one 1 to 2, and 2 to 3, this 2 to 3. సో ఇక్కడ మనకి అమౌంట్ హీట్ రిజెక్షన్ అవుతుంది కాబట్టి we are having this slight variation, right? From 3 to 4, that is the expansion device, and from 4 to 1. So this is a temperature change from TE to raised TE. Next, coming to the pressure and V. So here 1 to 2 isentropic, this is, so the 2 to 3, this is the expansion type, and this is again the isentropic compression type, that is 4 to 1. So these are the TS diagrams and PV diagrams of this simple standard refrigeration system. Got it? Isentropic compression, isobaric heat rejection, isenthalpic expansion, and isobaric heat extraction in the evaporator. Next, so now we will do some analysis for this simple vapor compression refrigeration system. So analysis చేస్తున్నప్పుడు, so work done comes into the picture, right? The work done comes into the picture. So here if you see the standard vapor cycle system what we have discussed in the last slides, so here what we see, it is carried out by the steady flow process. So taking some assumptions into consideration, so it is a steady flow process, negligible kinetic and potential energy changes across each component, and no heat transfer in connecting pipelines. So no heat transfer, there is no heat transfer in the connecting pipelines. Therefore, if we see the analysis for every component, so first we see the analysis in this vapor component, evaporator. So the heat transfer rate at evaporator of or refrigeration capacity QE is given by, and QE is equals to MI mass into H1 minus H4. ఎందుకంటే మనం evaporator తీసుకుంటున్నాం కాబట్టి evaporator లో the phase change is from 4 to 1. Therefore, QE is equals to mass of H1 minus H4, where M is a refrigerant mass flow rate per kg per centimeter, kg per second. H1 and H4 are the specific enthalpies. H1 and H4 are specific enthalpies, and the exit and the inlet to the evaporator. Therefore, H1 minus H4 is known as specific refrigeration effect or simple refrigeration effect. So what's the simple refrigeration effect? H1 minus H4 is the simple refrigeration effect, which is equal to the heat transferred to the evaporator at the evaporator per kilogram of refrigerant. So if you see the figure here, the heat is flowing from evaporator to outside, right? So that's why if you see the H1 minus H4 is a simple refrigeration effect, where the heat is transferred at the evaporator per kilogram of refrigerant. Now the evaporator pressure PE is a saturation pressure corresponding to the evaporator temperature. షార్ప్లో వెళ్ళి పడుకోవచ్చు కదమ్మా, హార్ప్లో వెళ్ళి కొంచెం హార్ప్లో. Next, if you see the pressure, so the evaporator pressure, the saturation pressure is equals to P saturation into temperature. Next, coming to the compressor. Okay, next component is compressor. The power input to the compressor WC, the power input. Why? Because the power input to the compressor WC is given by WC is equals to M mass of H2 minus H1. So if you see the compressor figure, so here the work is going inside, right? The work is going inside. The work we are doing at the compressor stage. Therefore, the work WC is equals to mass into H2 minus H1. Mass into H2 minus H1, where H2 and H1 are specific enthalpies at the exit and inlet of a compressor, and H2 minus H1 is known as specific work compression or simply work of compression. ఇక్కడ ఏముంది, ఇక్కడ H2, ఇక్కడ ఏం చెప్తున్నారు, H1 minus H4 is a simple refrigeration effect అంటే here H2 minus H1 is simply work of compression, which is equal to the work input to the compressor per kilogram of refrigerant. Okay, next one, the condenser. Next one is condenser. The condenser heat transfer rate at condenser QC, heat transfer rate at condenser QC is given by QC is equals to M of H2 minus H3. ఇక్కడ 3 ఎందుకు వచ్చింది? Because the stage is at third stage. That's why the heat transfer rate at condenser QE is equals to M of H2 minus H3, where H3 and H2 are specific enthalpies at the exit and inlet to the condenser respectively. Now, the condenser pressure PC is a saturation pressure. Therefore, PC is equals to P saturation into temperature. P saturation into the temperature, right? So that is at saturation time. Now the fourth one is expansion device. Fourth component is the expansion device. Here for the isenthalpic expansion device, the kinetic energy will expand. Therefore, at the control volume, the downstream of expansion H3 is equal to H4. Therefore, the KE is dissipated. The KE and the kinetic energy is get dissipated into various effects, and it can be written as dryness fraction. H4 is equals to 1 minus X4 of HFE plus X4 HGE is equal to HF X4 FG, right? Now see the coefficient of performance of this standard air refrigeration system is equal to QE divided by WE, that is equal to MF H1 minus H4 divided by MF H2 minus H1, that is equals to ఈ రెండు క్యాన్సిల్ చేసామంటే H1 minus H4 divided by H2 minus H1. Therefore, the heat rejection is equals to QK is equals to Q0 plus W, that is equal to H2 minus H3. COP for cooling H1 minus H4 divided by H2 minus H1. COP for heating H2 minus H3 minus H2 minus H1. Therefore, the refrigeration circulation rate M is equal to refrigerating capacity divided by refrigeration effect, that is Q by QP. So with this we'll stop the class. I have the other class in the next 5 minutes. So we'll continue the next class tomorrow at the same time. So thanks for listening the class. Have a good day.